So this lesson, I'll start there. State both forms of Newton's second law of motion. So, you should remember from the Newton's laws topic that we had two different ways of stating it. We could say the way that we remembered from GCSE and similar was that force is mass times acceleration, F equals ma. And we also had a different way of phrasing it, where we said that force was proportional to the rate of change of momentum, which we wrote in mathematical formula like F equals change momentum over change in time, dp divided by dt, or we could also write that as delta p divided by delta t, delta representing small changes. We're going to need that form of the equation for this topic. So, we're on impact forces this lesson. Our spec reference still the same, the section on momentum. We are down at the middle of there, looking at impact forces. Learning objectives. We want to describe what happens to the impact force and why if the duration of the impact is reduced. We want to calculate delta mv for a moving object that stops or reverses, and describe what happens to the momentum of a ball when it bounces off a wall. So, I'm going to try something. Let's see if this works. Aha, yes. So, how to throw a ball.
Succeed with your first two fingers on top and thumb at the bottom so it doesn't swing in the air. For an overarm throw, get into a side-on position with your target and point your non-throwing arm towards it with a straightened elbow. Turn down the thumb of your throwing hand and raise the arm behind you with the elbow above shoulder level. Lock your front leg as you transfer your weight onto it, creating a strong movement of the hips that brings your chest out to face the target. Swing your throwing arm forward and let both arms follow through behind the hip opposite to the throwing arm. To avoid throwing over the wicketkeeper, try getting the ball to the wicket in one pitch. Use a crow hop or a forward hopping motion to build up the lateral momentum of your body towards the target. For a quick...
So, interesting start. What I wanted to know was, how does that link to what we're doing now? So the question is, how would you throw the ball further? So, and if we thought about it, just ourselves, then we could say, well, perhaps we might choose to throw harder. Yeah, that makes sense. Follow through the throw. Do we notice the coach there talking and saying that the arms were spinning through and followed through with the motion? That's linked to what we talked about this lesson. So the whole thing with throwing, yeah, it was pointing the arm, throwing the ball, and both the arms followed through, almost like a windmill. There was the other way that he mentioned, was doing the little hop at the start to build up the speed. So that's making his speed increase at the start. What are we thinking of in physics? How would you give that ball a greater change of momentum? It's the same question. This is what we're thinking about there. We're thinking about how would we make that change in momentum greater? Well, throw harder, more force, a bigger force. Assuming that that cricketer throws it with as much force as he can manage, then we've only got a limited number of other ways that you could increase the range of that ball. So, for instance, more contact time. If he follows through with the throw, that ball spends more time in contact with his hand. Thus, we get a greater change of momentum. Also, with that little hoppy start, then he gets a bigger initial velocity to the ball. His body's already moving, so when he throws it, it's the momentum of him moving plus the momentum of the ball. So, the ball's initially stationary, then the impact force with the hand causes it to accelerate to speed v in time t. The gain of momentum of the ball due to that impact will be m times v, the momentum. we could say therefore the impact force is change in momentum divided by contact time, mv divided by t. If the ball is moving with an initial velocity u, and the impact changes its velocity to v in time t, then the change in momentum will now be mv minus mu. Smaller change of momentum. But we can say that change of momentum mv minus mu divided by t. Typical graph for that impact might look something like that. We looked at force time graphs last lesson. Notice this one's a slightly more interesting shape. It's got curvy bits. It shows that the impact force increases to a maximum and then decreases again during the impact. We remember that the green shaded area represents the impulse or change in momentum, and to find out that area we would need to find the area. So if it was a sensible shaped shape, like a square or a triangle, you could use a formula, like base times height, or for a triangle, half times base times height. That's not a sensible shape. We have to estimate. So to work out that area as an estimate, we would work out the value of 1 square. In this example, up and down, 1 square is worth 50. It goes from 0 to 50. And then sideways, it goes from 0 to 1 milliseconds. So it's 50 times by 1 times by 10 to the minus 3 milliseconds, giving us 0.05 newton seconds for each square. So each square is 0.05 milliseconds. If we count the number of squares that are under the line, or make an estimate of it, then we get a value for the change of momentum or impulse. So for this one, we're looking at something like 8 or 9, aren't we? It's around about that. We need to make a rough estimate. The average force of the impact can be worked out from the change in momentum divided by the contact time. So assuming we've worked out the area under the graph, we can work out what the contact time is by reading off the axes. It goes from 0 to 4.5. So if we said there were 9 squares underneath, 9 squares times by 0.05 is 0.45. 0.45 divided by the contact time, 45, gives us an average force of 0.1. I've worked that out wrong, haven't I? It's milliseconds divided by 1000 times by 1000 gives us 100 newtons. There we go, very easy, isn't it? A milliseconds mistake, isn't it? Always important to check your answer. Does that seem reasonable? If I got an answer of, like 0.1 as the average force, I've clearly got that wrong. So 100, the average force in that example. Yeah, that seems reasonable, because 100 goes through about 2/3 the way, doesn't it? So, for example, what if we got a ball of mass 0.63 kilograms initially at rest, struck by a bat, which gave it a velocity of 35 meters per second. The contact time between the bat and the ball was 25 milliseconds. Calculate A, the momentum gained by the ball, and B, the average force of the impact on the ball. A, the momentum gained. We're going to do P equals mv. The mass was 0.63 kilograms, the velocity 35 meters per second, giving us 22 kilogram meters per second. B, the average force. Force is the change in momentum divided by the contact time. The change in momentum we just worked out was 22. The contact time, 25 milliseconds. 25 times 10 to the minus 3, giving us 880 newtons. Very straightforward. We've got our formulas, P equals mv, and force is change in momentum divided by time. Nothing more complicated here. All we need to work out is where they get the information from in the question. So, what if the object hits a wall, for instance? If it hits a wall and rebounds, its momentum changes direction because of the impact, like in the diagram. Usually, if it hits if the ball hits the wall, normal to the wall, at right angles, its direction is reversed. So it hits it, bounces straight back again. Just like if you do an experiment with a ray box, you'd expect the ray of light to do that, wouldn't you? So its momentum is in the opposite direction. It has the same magnitude, but the opposite sign. So we could say that if velocity at the start is plus u, velocity at the end is minus v, u is going to be equal to v. The magnitude of u is equal to the magnitude of v, but they are just in the opposite direction. So what about the force? Change in momentum divided by the contact time, mv minus mu, but mv is in the opposite direction to mu, so it's got a minus sign now, but v is equal to u, so we're going to say minus mu divided by t is minus 2mu divided by t. So that is the change in, that is the impact force of the wall on the ball. Assuming that there is not a loss of speed on impact, we'll talk more about that next lesson, about what sort of things that implies. What if the ball hits the wall at an oblique angle? It's not perpendicular. Well, then we've got to find the component of velocity normal to the wall. So remember, we could split up the components of that u, the initial velocity, into a component that's going towards the wall and a component that's going parallel to the wall. We'll find that the parallel components do not change. It keeps going parallel to the wall at the same speed, but the normal component will be in the opposite direction. It's got the same magnitude but opposite sign. So the normal components before and after will be plus u cos theta and minus u cos theta. So the change in momentum in this case would be p equals minus 2 mu cos theta, by finding the difference between those two values above and multiplying by the mass. Again, assuming there is no loss of speed on impact. So, considering that's it for this lesson, I want to know if you've learnt anything new. Of this lesson, what is there that's new content? I'm not sure that anything is new learning. What we're trying to do is apply the things that we've got from the past few lessons to these examples. So the example of an impact. We already knew that force is rate of change of momentum. If we just call that force an impact force, then we've got that application, haven't we? We already knew about the area under the force time graph, and we already knew that the area under the force time graph is impulse, which is change of momentum, and we knew the formula for momentum, mass times velocity. So I would argue, possibly no, we've not learnt anything content new. What we've learnt is, yes, some new applications for the content that we knew. There'll be some questions on this underneath. Thanks very much.